Now we're going to discuss Python's hashed data structures. And one of those data structures is a set. A set, first we'll show a set at work, and then we'll learn something about how it inserts and retrieves things in nearly constant time. It's pretty fast. So to that end, I'm going to go ahead and populate myself a farm. So here is a sheep, and I'm making a list. And here is a sheep again. And now let's put in a cow, a horse, a pig, a goose, a pig, and then we'll add in another cow. Moo. Okay. There's my farm. Now I'm going to type animals equals set of farm. So we got something back. Did I type pig goose? Oh, I did type pig goose somewhere. So I have a pig goose. But you will see here, the type of animals is a set. All the duplicates that were in our initial list have been eliminated. You can cast a set back to a list if you wish. In fact, a common trick is to take a list that's got duplicates in it, cast it to a set, cast it back to a list, and you'll have a list containing no duplicates. Okay, now, one thing that is required, one thing you cannot do is something like this. Say I go, I'm going to put a mutable element in my list. So I'm going to say x is equal to, say, 1, 2, 3, 5 cats. True. All right, there we go. So here's x. Now I'm going to try to go set of x. Uh-oh. A list is an example of something that is not a hashable type. Now you could put a tuple in there. If I could change this, I could come in here and put in a tuple. And I say set of x. And that's perfectly fine. The order of things got scrambled around. But sets are sort of disorderly. They don't care about order because something's going on underneath that we need to understand. So there's this business of something called hashability. Watch this. If I do something like hash of 5, oh, that's interesting. Hash of 1,000. Hash of 10,000. So there's a function called a hash function that is defined on a lot of Python objects. And here's what a hash function is designed to do. It's designed to have two properties. One, it's almost impossible to tell what the original object was from its hashed value. So it's impossible to find any kind of inverse for it. And two, even if you could find an inverse, and here's another thing. It is possible that two objects might hash to the same thing. And that sort of generates a problem. But let's talk about that a little bit more as we go along. First of all, in. Let's talk about in. Say animals, sheep, Let's try sheep in animals. Sheep is said to be an element of animals because it belongs to the collection named animals. Now let's try this. Sample is equal to goose and cow. All right. Oh, and we goofed up our goose, didn't we? Let's see if we can add goose in. Oh, look at that. So now we do have a goose. Okay, so now what I'm going to do is I'm going to do this. Animals dot is subset of sample. That's false because every animal is not in the sample. However, the other way around, every sample element is a member of animals. So that evaluates to true. Now, one kind of cool thing Python does is you can do this instead. And this. And the reason the strict inequality holds is because there are elements of animals that are not elements of sample. So the relational operator less than or equal to is a subset relationship. Now here's another interesting thing to see, something called a difference. Let's try this. Let's try animals minus sample. What happened? What's returned to you is everything that's in animals but is not in sample. That's called a relative complement or a set theoretic difference. If I go sample minus animals, that's going to be an empty set because everything that's in the sample is in animals. So when you take away all animals and samples, what's left? Nothing. You have an empty set. So this is an example of where you see the empty set. Now we have two other operations on sets, or two operations. Yeah, this is one operation. It's an infix binary operation, set theoretic difference. There is union and intersection. And to do that, let's go ahead and do this. Let's create 1, 2, 4, 8. That's A. B is going to be 1, 3, 9, 27. So let's try A dot union of B. What is that? That's the combined elements in the two sets. A dot intersection of B yields only 1 because the two sets only have one thing in common. What they have in common is 1. Now here's another interesting little item. A dot symmetric difference of B. What is that? That's everything that is in exactly one of A or B. That's basically an exclusive OR. Now, there's some alternate notations. If you go A pipe B, there's your union. A ampersand B, There's your intersection, and A, and I think we can go hat B. Yes, that gives us the symmetric difference. So we have symmetric difference. We also have something called difference. Oh, we can also do this. A dot difference of B is the same as A minus B. Okay, you get exactly the same thing. But notice the order in which they're presented is not necessarily numerical order. We also saw we can add elements, okay, and we can get rid of elements. Let's go to animals. The pig goose was something I didn't really want. If I don't want it, I can discard it. Let us discard it. So I'm going to say animals. And the pig goose is now discarded. If you want to get rid of all of the animals, bye-bye. Everybody's been sent packing. Okay, so here's some things for you to think about. What do you think is underscore disjoint does? It's a method. Does pop work here? What kind of things can you cast a set to? And what happens if you try, well, let's try indexing into a set. That's an easy enough thing. Oops. That simply does not work. Okay, so we have a hashed structure here called a set. And that hashed structure does not keep track of order. So how roughly does this work? I'm going to describe it in words because it's complicated. Essentially, the only thing you can put in a set is a hashable object. And to tell if something's hashable, all you have to do is say hash of true. And if that's defined, that's a hashable object. True is hashable. Booleans are hashable. Lists are not hashable, because if you try to hash 1, 2, 3, you will get unhashable. If you try to hash a tuple, oh, 1, 2, 3. That's hashable. You get some big, hairy integer. Okay? And here's the general idea. What you have, what you do to make retrieval of things from a set fast is you use a very large chunk of memory. And then what you do is when somebody adds something to the set, the hash function is called, you figure out what the hash is, you mod out in such a manner that you're within the range of the size of the array that you've created, and whatever index comes out of that mod, you're going to plunk that object right there. Very nice. But there's a problem. And the problem is this. A perfect hash function never hashes two objects to the same value. Sadly, reality doesn't work that way. So how do we get around it? What happens is in this big array, which is called a hash table, we actually make a list at each entry. So if two things hash to the same value, you just pop that on a list. The problem here is when things get crowded, those lists might get fairly long and you waste a lot of time searching through those lists. But Python's pretty smart. It figures out when the load ratio, which is the number of occupied slots in relation to the size of the hash table it has created, gets large, it makes a new bigger hash table, rehashes everything, modding out by this new bigger number, and distributes it more sparsely in the table. So when you go to check and see if something's in a set, whatever you're asking to see if it's in the set, whatever element you're checking, it hashes that element. It goes to the address according to the hash function and looks through the list there, or maybe there's just a single item. So the retrieval time from a set is relatively quick. But this is, in general, you will find that mutable objects are not hashable. Why? Because a good hash function depends on the state of the object. And the problem is, if you have a mutable object, its state is different at different times. And that's not a good thing at all. So now you know about sets. Sets include things once, or they include them not at all.